इसके अंदर मौजूद
सारे इसके अंदर मौजूद
ठीक है। आप बैठ जाइए, चेयर इधर ले आना, बैठना अच्छा नहीं लगता मुझे।
यहाँ कोई मसला नहीं है, ठीक है।
इधर इधर आ
वो
जाए,
साथ ही हैं बस,
हाँ,
ज़्यादा जगह
इधर पीछे आ जाए ना, बैठे आना सामने खड़ के ना तुझे एक्सप्लेन करो। मल्टीमीडिया ऑन है वैसे भी।
इतना टाइम नहीं फिर चलो सर 5-10 मिनट जैसे बिस्मिल्लाहिर्रहमानिर्रहीम। We are discussing as a density function theory. What is density function theory? Basically, density function theory is a tool which is used to predict the properties of the material such as electronic properties, optical properties, and thermodynamic properties. When we use or deal the density function theory, we face some problem such as many body problem. When we deal the complex material, we deal many complex compounds such as your material CH2CH4. Initially, when we take starts from the Schrödinger wave equation, which is the important tool to discuss the density function theory. As we discussed the Schrödinger wave equation is beneficial for the use of to solve the Schrödinger wave equation for the finding of the electronic and optical properties of the material by means of Schrödinger wave equation. When we discuss the complex material, then we go to the complex compounds. So we cannot solve the Schrödinger wave equation for the complex compounds. So for the solution of complex compounds, we take aid from the density function theory. What is density function theory? Density function theory is a theory which is used to determine or predict the optical and thermoelectric and electronic properties of the material. In our case, we predict the optical, electronic, and thermoelectric properties of CH2CH4. For this, we use the tool which is known as DFT to predict the properties of this material. First of all, to the very important parameter for the prediction of the electronic properties of the material, that's in electronic properties we are familiar either our material is metallic nature, semiconducting nature, or insulating nature. So for finding the nature of the material by using the DFT, first of all we find the band structure of the material which is incorporated in the electronic properties. In the electronic properties, we use the band structure and also density of state. Band structure is a band in which we find the by means of DFT whether your material is metallic, semiconductor, or metallic nature. First of all, we discuss the band structure. In the band structure material, इसको थोड़ा कम कैसे करेंगे, आधा एक ही पेज पे आ जाइए ताकि इधर प्लस माइनस नहीं होता ये अच्छा। We use the by means of band structure we can predict the electronic properties of the material such as from the figure we can see that it is the band structural band profile of the material CH2CH4. First of all, we discuss the main parts of the graph, and the long x-axis we take at the symmetric points. These are the symmetric points. What are symmetric points? Symmetric points are the points lying on the brilliant zone. What are brilliant zone? As we discuss the material minutely or microscopically, we can discuss the crystal structure. In the crystal structure, atoms are placed in randomly, and some materials we have discussed, some atoms are placed in a regular pattern. In DFT, we use a regular pattern from the CF file. CF file in Win2K, by using the DFT in Win2K code, we use a CIF file. CIF file is a crystallographic information file in which the number of atoms are placed in the crystal file in the periodic way. In the periodicity of the crystal structure in our material, we use a brilliant zone. What is brilliant zone? A brilliant zone is a zone in which a regular pattern of atoms we have discussed. In the brilliant zone, all the atoms are giving the maximum properties of the material such as diffraction, polarization, reflection, extinction coefficient, and many properties. So in the crystal structure we make a zone. That zone is called brilliant zone, and these symmetric points along x-axis, as you shown in the figure, are lying in the brilliant zone. So the reason to discuss these symmetric points in the brilliant zone, because in this symmetric points the maximum properties of the brilliant are absorbed as shown. Along x-axis, along y-axis, we take energy in terms of electron volt. What is this energy in terms of electron volt? Basically, this is the energy in terms of electron volt of the your material present in these spaghettis, in these energy levels, in these energy orbitals. So we can say that band structure is the relation between the symmetric points of the material of your material, of symmetric points on the lying on the brilliant zone of your point, and the energy of the electron present in your material. It is the profile which discuss the energy of the electron, energy in terms of electron volt of your material and the symmetric points lying on the brilliant zone. So we discuss the main components of the brilliant zone. This dotted line is known as Fermi line or Fermi energy. Basically, this Fermi line distinguish the two main parts of the brilliant zone. The first one is the valence band and the conduction band. And the valence band, as you know, these valence electrons are basically lying in the field of the nucleus. So these valence electrons lying in the field of nucleus, so we take as the energy in terms of negative sign conventionally. And above the Fermi level, these electrons are known as conduction electron, and these conduction electrons are not bounded in the field of the nucleus. So these conduction electron, we can say, are free from the nucleus are free from the field of the nucleus. So Fermi energy or Fermi level is also discussed as it is the ground state energy of your material. It means all the valence electrons are lying in the ground state energy. It also can say that at the Fermi level, it is the maximum energy level of the valence band. So these lines R, tau, x, m, and t, these are the symmetric points or k vectors lying in the brilliant zone. And the brilliant zone is your main concern in your crystal. In brilliant zone, we can say brilliant zone is that region in which you have maximum number of orbitals, maximum number of energy levels in which you discuss your material. So by means of band structure, we can know the nature of the material. First of all, if these energy orbitals are overlapping or crossing the Fermi level, and these spaghettis are Fermi level are also crossing the Fermi level, so we can say that our material is metallic. If these spaghettis or orbitals of the valence band and the conduction bands are overlapping inside the Fermi level, we can say that our material is metallic. If the spaghettis or energy orbitals does not coincide, does not overlap the Fermi level, either they are valence band or conduction band, so we can say that there is some energy gap. If the energy gap is present, so our material becomes semiconductor or insulator. Its value depends upon the energy band gap of your material. If the energy band gap is below the 3 electron volt, then your material becomes a semiconductor. If the band gap value of your material is greater than 3 electron volt, so you can say that your material is an insulator. In this case, first of all, to find the nature of the material, we can see the direct band gap or indirect band gap. If the maximum is the maximum of the valence band lying on the same symmetric point, and the minimum of the valence band also lying the same symmetric point, then we can say the band gap is direct band gap. If the maximum of the valence band does not lie on the same point of the symmetric point, or the maximum of the does not lie at the same symmetric point, so we can say that the band gap is indirect band gap. In your case, you can see that the minimum of conduction band lying in the x point, and also the maximum of valence band lying in the same point, that is the symmetric point of your brilliant zone. So we can say that to find the energy band gap of the material at 0 to minimum about, you can say that 3.3 3.8. So the energy band gap is about 3.8. You can say that your material become an insulator. And sometimes we can also, when we dope in CS2 CH3 of some impurity, this insulator or semiconductor become metallic nature or semiconducting nature when you dope in this your material. ठीक बस ये इसमें ठीक हो गया.
मतलब इसमें अब ये कहेंगे कि हमारा जो ये मटेरियल है ये वो इंसुलेटर इन नेचर है।
इंसुलेटर भी क्योंकि 3 से अगर ये 3 से अबव होगा ना
3 से अबव हो
तो फिर ये सेमीकंडक्टिंग इंसुलेटर में जाएगा.
और इसमें सिर्फ वो लाइन डिस्कस करेंगे जो ओवरलैप कर रही मतलब इसका
जी, जी,
मैक्सिमम और बाकी अब जो ये वाली साइड में इनमें नहीं कर रही तो इसको नहीं छूना
नहीं करेंगे. ठीक हो गया.
तो डायरेक्ट इनडायरेक्ट बैंड गैप का कोई फायदा या नुकसान?
डायरेक्ट एंड बैंड गैप में आपके पास जो इन योर डायरेक्ट बैंड गैप नेचर योर वैलेंस बैंड मैक्सिमम एंड वैलेंस बैंड मैक्सिमम एंड कंडक्शन मिनिमम लाई इन द सेम सिमेट्रिक पॉइंट. सो इट मींस your electronic transition from valence band to conduction band is easily as compared to indirect band gap.
Indirect, yes.
Because the momenta of your material which is moving from valence to conduction band is lying at the same symmetric point, it does not consume maximum energy to move from valence to conduction band. And when the indirect band gap is lying on your material, it means the electron has maximum energy to jump from valence to conduction band and to for indirect one symmetric point to another symmetric point.
डबल एनर्जी
ठीक है. हाँ मेरा अगली आगे आप एक्सप्लेन करें जल्दी से. कंडक्ट वो वाली क्या कहते हैं ऑप्टिकल जल्दी.